Welcome to Algebra 2. We're on section 1.3 today, modeling with linear functions. All right, our introduction for today. We've got 4 different graphs, and each describing a different situation happening in real life. And what we need to do is decide which graph is modeling each situation. So let's look at the first situation. A person gives you $20 per week to a friend to repay a $200 loan. Okay, an employee earns $12.50 an hour plus $2 for each unit made per hour. And then number 3, a salesman receives $30 a day for food plus 56.5 cents for each mile driven. And number 4, a computer bought for $750 depreciates at $100 per year. All right, so as we kind of look here at the first graph, here I notice that I'm starting off at a height of 30 and then slowly increasing. Okay, so where do I see a 30 value and then something tacked on to that? So $30 a day for food and then 56.5 cents for each mile driven. Well, this would show that $30 a day for food, and then as he drives more and more miles, he earns more and more money on that business trip or whatever. Okay, so I'm going to say that letter A goes along with option 3 for situation 3. Letter B, here we start off with a height of 200. And then as we move on and on and on and on, eventually we work our way down to 0. Well, starting off at 200, the only one that I see $200 in is a $200 loan, and then a person gives $20 per week. So as this person is paying back the loan, the amount that he owes is going down. So if he starts off owing $200, and then as he keeps paying $20 per week, the amount he owes is going down. I'm going to say that letter B goes with option 1. All right, letter C. Here we've got this graph, and it looks like we're at about, I don't know, this would be 15, so maybe 12.5, and then steadily increasing from there. That certainly looks like option 2. An employee earns $12.50 an hour, and then as more and more units are made, that employee earns more and more and more and more. That gets number 2. And then letter D, a computer bought for $750. So initially time 0, $750. We can see that represented in D. That makes sense. And then it depreciates, so its value is going down as time goes on. So just before 8 years are up, that computer is not worth anything anymore. So 4 is D. Those make sense. The idea is to take real-world information and be able to chart it out, interpret where the numbers are coming into play in the graph. And you'll notice that we saw the word per a lot. So $20 per week, and that was indicative of how steeply that line was going down. An employee earns $12.50 an hour plus $2 for each unit made. That could have very well said plus $2 per unit. Okay, and that showed what we saw in letter C here, that as the units went up, that line's sloping up, positive $2. Salesman receives $30 a day for food plus 56.5 cents for each, again, per mile driven. So that's giving us a little bit of a look at slope of that line. And then computer bought at $750 depreciates at $100 per year. So as every year goes on, you can see we're climbing down $100 each time. It's rise over run. That word per is indicative of the rate, the slope, the steepness of that line. All right, 3 linear formulas that we have. We covered them in our algebra refresher packet, but they're just here for your reference. We've seen them in Algebra 1. We are definitely going to use those today. Then we get to this slide on lines of best fit. Sometimes you won't have a situation in real life that directly models a perfect line. You've probably seen this in science class when you are conducting experiments and graphing your results. A line of best fit is just a linear function that we can put on a scatter plot and predict, again, predict, not know exactly, but predict what would happen at future times or for different situations. The correlation coefficient R is a number from -1 to 1 that measures how well a line fits a set of data points. So this is mainly for use with a calculator. Your calculator goes through an amazing process to calculate a line of best fit. We'll go through an example of that. And it will also tell you the R value that goes along with it. So it will tell you how accurate that line of best fit is. All right, so our first example, we've just got some graphs and we need to write an equation of a line and interpret the slope. So we had better see something using that per or for each language. So for number 4, here you can see our y-axis measures the fuel in gallons, and the x-axis measures the distance traveled in miles. So this is you can see the header there, modeling what's going on in a gas tank. Well, if we wanted to write the equation of our line, you'll notice that we know this y-intercept. We also know, based on the 2 points that we have, this point right here would be the point 0, 90, or sorry, just 0, oh, hold on a second, 2, 4, 6, 8, 10, 12. That would be the point 0, 12, Mr. Hearts. And then this other point, we have 99. So we have to calculate our slope. Our change in y, we go from a height of 9 at our second point, right? The line's going this way. So our y2 is 9. Our y1, we started off at 12. So 9 minus 12 over what happened in our x direction. Well, we ended up with 90, and we started off with an x value of 0. So our slope is actually -3 over 90, -1 over 30. And since we know the y-intercept is 12 right there, the equation of our line is y equals -1/30 x plus 12. Right? Interpret the slope. So our slope is -1/30. Well, what does that mean? The rise was our y-axis, our fuel, our gallons. The x-axis, our run, was a distance, miles. So the slope is telling us -1/30. Car is using 1 gallon per 30 miles. You could also say that the car is getting 30 miles for every 1 gallon as well. Let's look at number 6. Here we've got tree growth. The height of a tree in feet. We've got the point 0, there, probably when it's first planted in the ground as a seed. And then after 4 years, you can see we have a tree that is 6 feet tall. So we've got this other point over here that is 4 years, 6 feet. Again, we need to find the slope. And we could probably count out rise over run here to get a good estimation. Our y2 minus y1 over x2 minus x1. Slope is +3/2, and that agrees with our graph. It's rising to the right. We should have a positive slope, which is different than what we saw in our last example, falling to the right, and that showed a negative slope. So this does make sense as we go along. Our y-intercept is 0, so y equals 3/2 x. So our slope of 3/2, that tree grows 3 feet per 2 years, or we could say 3/2 feet per year. Just as before, sorry, in number 4 here, we could say the car is using 1/30th of a gallon per mile. Okay, so our slope is telling us per unit, per year, per mile. Example 2, this is kind of an involved one. While on vacation in Canada, you experience the metric system. You notice temperatures are measured in degrees Celsius instead of Fahrenheit. From science class, you remember that water freezes at 0 Celsius and 32 Fahrenheit, and water boils at 100 Celsius and 212 Fahrenheit. Nice little shout out to the chemistry department there. Write an equation that represents F in terms of C. Well, in terms of, it's just telling us what our outputs and inputs should be. So we want F to be our output in terms of C, our input. So if we plug in some degrees Celsius, it will tell us what the degrees Fahrenheit are. Well, let's just imagine that we were graphing this thing out. So outputs and inputs are the same as X's and Y's, right? So what we would have is a graph where our inputs are degrees Celsius and our outputs are degrees Fahrenheit. So the Fahrenheit, the output's acting like the Y, the Celsius is our input, it's acting like X. So now if we look up above, that 0 and 32, well, that represents that if I had an input of 0 degrees Celsius, I would get an output of 32 degrees Fahrenheit. And since that X value, or C value in this case, is 0, that is going to be our Y-intercept, or our F-intercept. But that's really useful. That's going to be our plus B in our Y equals mx plus B. We've also got the point that if our input is 100 degrees Celsius, that is 212 degrees Fahrenheit. So now we're able to calculate the slope. Right? We've got our Y-intercept already. If we get the slope, we're set. And we've got 2 points to do just that. My y2 minus y1 over x2 minus x1 gives me 180 over 100, which is 18 over 10 if we simplify, and we can simplify that even further, 9/5. So now my y equals mx plus b is 9/5 x plus 32. Okay? And in order to help us remember, we might want to call this Fahrenheit equals 9/5 whatever Celsius is plus 32. I love this example because it makes you think of inputs and outputs. That's fantastic. So the temperature is 22 degrees Celsius outside. What would that be in degrees Fahrenheit? So we're trying to find our Fahrenheit output, and our input is 22 degrees Celsius. Well, that Fahrenheit temperature is going to equal 9/5 times 22 plus 32. All right, so now we're back to fractions. We could use a calculator here. 9 times 22, oh boy, what would that be? 180 plus 18, 198 over 5 plus 32. That would be 150 plus 10, 160 over 5 if we get a common denominator. And that takes us to 358 over 5. And if we divide out 358 divided by 5, we get 71 3/5, or 71.6 degrees Fahrenheit. It's always so cool to me to see, because you're so used to seeing 22 degrees and you like shiver immediately. But in Celsius, that's actually pretty comfortable. All right, letter C. Rewrite the equation in A to show C in terms of F. So now we're just switching our inputs and outputs. All right, so let's see. Now our situation is Fahrenheit as inputs, Celsius as outputs. So I've got the point 32, 0, and I've also got the point 212, comma 100. And we could go through the same process that way that we did before. Or what we can do is we have this nice equation. Why don't I just reconstruct what we got in letter A so that we have C equals something F? I think that might be a little bit faster. So if I'm going to solve that one for C, I'm going to first start by subtracting 32 from both sides. And then I want to divide out that 9/5, which means I multiply by the reciprocal, 5/9. Okay, and if we distribute, we find that Celsius is 5/9 Fahrenheit minus 32 times 5, again, there's 160 over 9. So there's our formula. We would have arrived at the same thing had we gone through this process over here using our 2 points. But the important thing to realize is now I've got something that if I plug in some degrees Fahrenheit, it will give me degrees Celsius. Letter D says the temperature of the hotel pool is 83 degrees Fahrenheit. Just right. What is this in degrees Celsius? So we take our new function and say, hey, we want Celsius as an output. That equals 5/9 times 83 degrees Fahrenheit minus 160 over 9. All right, and what that's going to equal is 5 times 83, which is 415, minus 160 over 9. Okay, luckily that keeps a common denominator. And 415 minus 160, oh, what would that be? 255 over 9, which equals, oh, let me think, if it were 270 over 9, then that would be 30. So I've got to take away a couple sevens from that. Be 263. 256. And 249. So it would be 26 and 3/9, or 26.33 degrees Celsius. I'm just going to check that on the calculator really quickly. .33, I'm sorry. Yeah, I just had to take away 2 9s. Okay. All right, moving on. Determine if the data points show a linear relationship. If so, write the equation of a line of best fit. Estimate y when x equals 15 and interpret its meaning. So this is a problem where there's a lot of estimating involved, and depending on what we consider a line of best fit, there are several different correct answers that could work. So let's plot the points and see what we come up with. So my x-axis is measuring months, and you'll see they're all positive. And I need it to go up to 23. So if I'm setting up my x-axis here, I may want to adjust it so that I have a little bit of room off to the left. I'm just going to draw a new set of axes here. And the hair length, I don't think our hair is going to retreat back into our head. So at 9 months, just going to label my axes here. Well, that doesn't fit our data very well when we count by ones. That would only get me up to 20, so I'm going to have to go by twos, I think. Let's retry this x-axis here. Okay, and I hope this gives me enough of a readout here. So at 9 months, we have 3 inches. So here's 9 months, 3 inches. At 13 months, we have 5 inches. At 18 months, we are at 7 inches. And at 22 months, we're at 10 inches. And at 23 months, we're at 11 inches. So right there. And this is going to be kind of tricky for me to do on the smartboard. But I'm going to see if I can't find 2 points that approximate that data pretty or a line that approximates that data pretty closely. I'm going to kind of sketch in a line of best fit. And then now to find the equation of this line of best fit, what we need to do are find 2 points on that line that appear nice to work with on our grid. And I'm not really coming up with any incredible winners here, but maybe here it looks like we've got a nice clean crossing. Remember, we were counting by 2s. That would be the point 15, 15.6, just by approximation. And then another point that appears to cross well is here, maybe. That would be 21.9. Okay, so using this, we can come up with the equation of a line, and I see that I kind of made a silly little progression there. So if we have our 2 points, then our slope, y2 minus y1 over x2 minus x1 gives me 3 over 6, which equals about 1/2. Again, we're just using this to approximate. So now I can take one of those points. I'll use 15.6, run through my point slope form. Y minus y1 equals m times x minus x1. And I get 6 equals, let's distribute. And let's add over our 6, which would be 12 halves. Y equals 1/2 x. And that looks like it's going to be minus 3 halves. And again, that doesn't really make a whole lot of sense. Our y-intercept, which would mean that after 0 months, we have negative 1.5 inches of hair. Excuse me. But the point is, we've got this function that will approximate, it will estimate the inches, the output of hair, given a number of months for an input for x. So if we wanted to approximate at 15 months, we would simply say, okay, y, the output, is 1/2 times 15 months minus 3 halves. 15 halves minus 3 halves, and we get approximately 12 halves, or 6 inches of hair. Okay, and that means 6 inches of hair after 15 months. But again, we should have known that made sense because one of the data points that we chose, or one of the points on our line of best fit, was 15.6. All right, next one. Use a graphing calculator to find an equation of a line of best fit, and then we want to use that calculation result to interpret the correlation coefficient. So give me a second. Here we've got our calculator. And to input this set of points, we actually have to find all of the x coordinates and the y coordinates. And we want to be sure that they match up. So how we're going to input this, you can see there's a stat key here. And what that stat key does, see if I can't focus a little bit better. Oh, that's much nicer. Stat, I can edit my list of numbers. And here I'm just going to clear out these lists right now. And my first list has to be my x values. So I'm just going to kind of go through these points left to right and just calculate all the x values I see. So I've got an x value of 0 for that first point, then an x value of 1, 2, I've got an x value of 3 and another x value of 3, then an x value of 4 and an x value of 5. Now I'm going to hit the right arrow key to enter in all my y values. So I had the point 0, comma 4, I had the point 1, comma 4, 2, comma 3, 3, comma 3. I also had 3, comma 2. And then I had 4, comma 2, and 5, comma 2. So you can see every time I read a pair there, like 5, 2, that was one XY ordered pair for those points. All right, once I have that, I'm going to go back into the stat menu and then toggle over to calculations, and then option 4 is a linear regression. Well, we're talking about a linear function that models these equations. They have a correlation of best fit, a regression equation, so it's going to calculate what the best fit line is precisely. So if I hit enter and enter, you can see there it gives me that output. So it says that the equation of that line should be y equals negative 0.4758x plus 4.08. And then you can see right here is our r value, and that's negative 0.908. You know, it's pretty close to a negative 1. That's indicating that we should have an equation of a line of best fit that is a pretty good approximation, and that line's going to have a negative slope. That's exactly what we see based off our graph. So the calculator, very, very useful tool, very neat how it can handle linear regression. Now, furthermore, that's not asking us to do this, but just to show that the calculator can do so much. In our y equals menu, here I still have some entries from a previous example, so I'm going to clear those out. Under y1, we can hit the variables key, vars, right under the arrows. And you can see down option 5 is statistics. That's what we're working with. And toggling over to the right, option 1 under EQ is our regression equation. So if I hit enter, it types in that equation that it found to be the line of best fit. Now before I graph this, if I go to second and then y equals, you'll see it says stat plot. Plot 1 is turned on. We want to make sure that is the case. Plot 1 being turned on, what that will do is that will plot all of those points that we entered in all the x's and y's for. So then I hit graph, and you can see it shows the points and the line going through. And it certainly does look like a nice line of best fit there for us. Sometimes you will not see the points show up on your screen, particularly if you're working with examples where maybe you don't have nice little ordered pairs, but you've got huge numbers representing costs and miles driven and things like that. If that's the case, you can always hit this zoom key, and then one of your options, if you toggle through that menu, is option 9, zoom stat. That will adjust the window to fit all the points that you've entered in your list. So pretty neat how that does calculate the line of best fit, and it's a very nice line of best fit for our points here. All right, love seeing what that calculator can do. All right, our last example. Write the equation of the line that passes through 8, negative 5, and it's perpendicular to the line y equals negative 4x plus 1. Now you folks are at a distinct advantage because you've just come off of geometry and you know what perpendicular means. So let's just say we were drawing in our original line, negative 4x plus 1. So we would have a line that looks like that. All right, and if we want a line that's perpendicular, look at this one. It is very steep and very negative. And we should know from geometry that if it is perpendicular, it's going to make a 90-degree angle. So if we want that to happen, we need a line somehow that is rising to the right. It's a positive slope, but it's also pretty shallow, right? It's not nearly as steep as that red one. So what we want to do is we want to take this line that has a shallow positive slope and just kind of adjust it so that we get to this point 8, -5, so that our line passes through that point as well. Well, we know that if we have a point that our line that we desire passes through, then all we need is a slope for that line, and we know how to find that equation. Well, here we go. The slope of our given line is -4, and that's representing that steep negative slope. If we want a shallow positive slope, what we want is the opposite reciprocal. So the slope of our line that's perpendicular is going to equal a positive 1/4. Okay, it will always have an opposite reciprocal relationship when lines are perpendicular. That's how their slopes will compare. So now we've got our slope and we've got our point. Y minus y1 minus a -5 is the same as +5 equals our slope 1/4 times x minus x1, and that given x value was 8. And if we distribute that 1/4, 1/4 times -8 is -2, and then we subtract our 5 over y equals 1/4 x minus 7. And it certainly does seem like our graph would be really low on the y-axis for its y-intercept. So that does fit graphically with what we're trying to do. All right, and just like that, that's the end of section 1.3.